Hi, in this video, I will be going over our paper titled Data Efficient Multimodal Fusion on a Single GPU, which was selected as a highlight paper at this year's CVPR. We define multimodal fusion from the perspective of alignment, where the aim is to learn a single latent space that is shared across different modalities such as text, image, audio, and so on. But there is a huge barrier to train such models. Current approaches such as clip and align often require substantial computational resources and large-scale paired datasets. Our main goal in this paper is to develop a framework for efficient multimodal alignment that reduces computational resources and data requirements. Formally, given two modalities X and Y such as images and text, we aim to learn two networks, Fx and Fy, that map from samples in their respective modalities to a shared latent space S. Currently, contrastive learning has emerged as a prevalent objective for multimodal alignment. It aims to learn a shared latent space where semantically similar multimodal inputs in ambient space are encoded to nearby points in latent space, while dissimilar inputs are embedded further apart. Such methods are commonly trained with the symmetric info and C-loss. However, many methods jointly train both Fx and Fy end-to-end. This requires substantial computational resources and massive paired datasets of multimodal inputs which are expensive to collect and annotate. This presents an acceptable cost for many practical scenarios where access to compute is limited and where multimodal data is scarce. We aim to address these gaps in order to increase accessibility to such multimodal capabilities while also enabling scaling models to new tasks, domains, and modalities with fewer resources. We therefore propose our framework FuseMix, which addresses these limitations. The main idea behind FuseMix is to leverage existing pre-trained unimodal encoders and use modality-agnostic data augmentations on latent space to enable compute and data efficient training. Since FuseMix is agnostic to the choice of unimodal encoders, we can combine arbitrary encoders, making it a plug and play framework. We define our model F to be the composition of a frozen unimodal encoder G and a learnable lightweight fusion adapter H. Using pre-trained unimodal encoders, we can benefit from the rich modality-specific semantics that they already encode. Bootstrapping from them reduces the need for large-scale multimodal paired data. Since we aim to perform multimodal fusion with little resources, it is intuitive to also leverage data augmentations to generate synthetic multimodal pairs. We introduce a simple yet effective multimodal augmentation scheme on latent space inspired by Mixup that is agnostic to modalities and the choice of unimodal encoders. We take existing multimodal latent pairs from unimodal encoders and construct augmentations as random convex combinations while sharing mixing coefficients across modalities. Here we show PyTorch style pseudocode for training our FuseMix method. Our framework can be easily implemented in just a few lines of code as shown. We show that by using FuseMix, we obtain highly competitive results, which in certain cases even outperforms state-of-the-art methods in both image text and audio text retrieval tasks, while using orders of magnitude less compute and data. For example, we use 600 times lesser compute and 80 times lesser image text pairs than clip and yet are able to outperform it in recall for the text to image retrieval task. Additionally, we show that FuseMix can be applied to convert pre-trained text-to-image generative models into audio-to-image ones by aligning the latent space of an audio encoder into the latent space of clip. For example, the following audio clip produces the cat image shown in this figure. Since sourcing multimodal paired data can be costly, we aim to know how to allocate efforts to construct a dataset for multimodal fusion by quantifying three properties: quantity, quality, and diversity. We observed that while increasing quantity improves performance as expected, the quality of the underlying dataset has a huge effect. We find that we need as much as 6 times the number of image text pairs from web data, which are of lower quality, to match the performance of higher quality human annotated pairs. Finally, we find that with access to limited data, sourcing image text pairs that are maximally diverse provides substantial improvements of up to nearly 40% compared to selecting image text pairs without consideration for the diversity. We thank you for listening to our presentation.